Hello, welcome to my presentation. So this presentation is about the surprisingly simple maths underpinning AI. So obviously large language models were invented a few years ago, and for me I found it very annoying that I didn't actually know how artificial neural networks and stuff work. And when you try and research it, there's an infinite amount of information. There's all sorts of huge books on it. But what I eventually realized is that the actual most important concepts are surprisingly simple. And if you just learn and understand vectors and dot products, it gets you almost 50% of the way there to understanding artificial neural networks. So we're going to cover vectors and dot products. So cool. So what's a vector? So a vector is just a list of numbers. On the left, I hope you can see my mouse. Can you? Yes, you can. So on the left we've got it in, the mathematical notation. We're going to be doing some programming later, so you might see it written like this, but it's really just a list of numbers. Now, what do these numbers mean? Okay, so we're going to go over a simple use of a vector. So in this example, we're basically using a vector to represent a direction and an amplitude. So it might be something's trajectory on a two-dimensional plane, like an ant running across your desk. So the two numbers are always relative to zero, because in this example we're representing a velocity, right? So how much does it move along the x-axis and y-axis? Now this also gives us an amplitude, because although there's no explicit number for the amplitude of the movement or the size of the movement, you can obviously just calculate that with Pythagoras' theorem. So what else can vectors do? So a vector can have any length, and it can therefore have any number of dimensions. So if you wanted to represent trajectory in 3 dimensions, you would have 3 numbers. But we could have 8 numbers, 100 numbers. So here's an example of what you could do with it. So let's imagine you're running a dog shelter and you've got 100 dogs and you want to characterize your dogs. So you could find some characteristics that can be expressed using numbers. So in our example, age, weight, energy levels, vigilance, hair length, whatever. And each dog will have its own vector of numbers which represents its traits. So what's the dot product? So the dot product is the maths you can use to compare. Well, the dot product gives you your it allows you to compare two vectors, basically. I should have just read what I'd written. So we can compare two vectors to find out if they point in the same direction. And it gives us a number between -1 and 1. So if your output is 1, that means the two are identical. If the vectors are pointing in completely tangential directions, it will be 0. Similar directions might be like 0.86 or something, and if they're pointing in opposite directions, you'll get -1. So it just gives you any number between -1 to 1 to tell you to what extent your two vectors point in the same direction. Right, so the maths is actually very simple. So all we do is we've got our two vectors, which is our true list of numbers, and if you imagine them vertically, we just pair them up, multiply each pair of numbers together, and then we just sum all the results. So what have we got here? So normalizing, the mathematical notation makes it look very complicated. Sometimes I think that maths is some sort of conspiracy to make us think we're stupid, but it's not actually that complicated. So the normalizing part is not that important to what we want to explain, but I think I made a slide. Yeah, so normalizing, so we're basically making our vector have a length of 1. So let me just go back to the previous slide. So imagine basically so to normalize this one, we would basically be shortening this arrow but keeping it at the same angle, just so that it has a length of 1. That's what we're doing to normalize. We're just making all of our vectors have the same length. Why has it done that? So after it's normalized, it'll make the numbers smaller usually. Right, so this is the maths for the actual dot product, which is very simple, as I said. So you pair all your numbers up and you multiply them, and then you sum them all. So you just add all of these, and that's your dot product. Very, very simple maths. Cool. So to understand why dot products are cool, so dot products are not just useful for AI, they're useful by themselves. So we're going to do a bit of coding and implement a search database. This part. So what we're doing, so firstly, let's just implement a dot product, show a dot product in Clojure. So first we just need to make a couple of vectors with just made up data in them. Let's just swap some of these around and change some, whatever. And these can be, they don't have to be integers, they can be minus numbers or whatever. They're normally floating point. Cool, so one of the things I like about Clojure is it makes stuff like this very simple. So remember our algorithm, right? So we want to pair the numbers up between the two vectors and multiply them. You can literally just do that with map in Clojure. So that should literally be it. So 3 times 4 is 12, and 2 times minus 3 is minus 6, you see, so that's that. And the other part of a dot product is that once you've got all these numbers, you need to add them up. And in Clojure, you do that just with a reduce. So so the dot product of those two vectors should be 75.1. So let's save that as a reusable function, dot product. Oops. Cool. So the next thing we need to do, so remember I said that we need to normalize our vectors to make them comparable. Now for here I'm just going to copy and paste because the maths of doing this just isn't really pertinent to what we're learning. So here's one I made earlier. So this will normalize a vector. So when you normalize a vector, the numbers are going to get smaller because it's reducing the amplitude. So the amplitude, or the magnitude of the direction is, sorry, the direction of the vector. A vector is has a direction in multi-dimensional space, right? So we've got 5 dimensions here. So in 5-dimensional space, it points in the same direction, but it has its amplitude, the magnitude of the movement is normalized. Anyway, so Right, so yeah, so I think now we're at the fun part, right? So yeah, we want to make our database of dogs, and we want to implement a similarity search. So hypothetically, say a customer bought a dog, and then they come in next day and say, I really liked that dog and I want another one the same. So you want to be able to automatically search your database for dogs that are mathematically similar. So again, I'm going to pull a here's one I made earlier. So here's our little dog database with our dogs' names and a vector representing their traits. Now, like I said in the presentation, so these could be things like I can't remember, but different traits like its personality traits or its hair length or whatever. Yeah, cool. So we're going to make a function called similarity search or something. It's exciting. So yeah, basically what we need to do is for each, right, so our inputs for this function, okay, so hold on, we need a normalized version of our database, right? So db norm, okay, let's move these functions to the top since they're sort of basic functions that we need for everything else. And let's delete these because we're not using those anymore, we're using our new database. Okay, so we're making a normalized version of our database, and we do that just by wait, why is my spelling different here? Did I test this normalize? That can't have worked. Oh, I know why it worked. It's because yeah, I'm not going to explain why that worked, but I know why it did. Anyway, so our normalize function, yeah, so we need to normalize our DB. Okay, so we've got an error message. So we need to, because our database has keys and values, right? So our key is the dog's name and our value is the vector. So we need to do apply in or apply vals, that's it. Apply vals, normalize DB. Update vals, no? Don't know how to create a sequence from normalize. Ah, they're the wrong way around. Cool. So we should cool, so we've got our normalized database, right? The formatting is a mess, but that is correct. Cool. Right, so for our normalized database is going to go in as an input. And the other input is going to be the profile for whatever dog we're searching for, right? We're searching for a dog based on its traits. Right, so we can use our for loop to search for. Okay, so we've got a map. So we need to split it up into key and value. So key is name and value, we'll call it vec. So we just need to calculate our dot product of the profile we're searching for and our vector, right? And then we need to put that inside a new so name. So we're creating a new hash map for, right? So we should get basically a new data structure, which is a list of the dogs' names and their scores. 4 requires an even number of forms. Oh yeah. Cool, so we should be able to do, this isn't finished, but let's just see what it does so far. So we put in our normalized version of our DB, and we need to put in the profile of the dog we're searching for. So let's just make one up, right? So let's just like trivially modify one of them. So we're expecting it to find oh, whatever, it doesn't matter. So what will happen if we do that? So no, we haven't done this quite right because we forgot to normalize this, right? So whatever we're putting in, normalize. Right, so in theory, this should find the doggo that's the most similar. Oh no, so it's given scores, right, but we haven't sorted it. So to sort, we just do sort by score. Okay. What order are they in? Okay, they're backwards, right? But how do we make it sort forwards? Cool, so in theory, Vespa should be the most similar dog. Is that right? Yeah, it is. That's the one we modified, right? We just took Vespa and made some small changes to it. Cool. So yeah, this is a use of dot products, which is very simple maths. And you know, this could actually be useful, right? Obviously here we've only got 6 dogs and each of them only have 5 traits, but you can imagine a situation where you would have 300 dogs and instead of 5 traits maybe you've got 15. And doing a similarity search like this without a computer's assistance could be very difficult to do. So yeah, that's dot products and why they're useful, and it's honestly really cool. And all of the code here just fits in one page. Didn't need to use any external libraries, just using the Clojure standard library, basic maths. Cool, so I hope that's impressed why dot products are fun. So let's go back to the presentation. So how do you make it continue from where we were? We need to press Shift and F5 to continue from the current slide. Shift F5. Right, cool. Right, artificial neurons, right. Cool, so the cool thing about artificial neurons is that they are powered by dot products. So yeah, I'll just read off the screen because it's probably better than whatever I can remember. So an individual biological neuron both stores information and also processes it, right? However, computers aren't architected like that. So in a computer, data and processing are separate. You've got your bank of memory, also known as RAM, and then you've got your processor, and information has to move between them. However, although each neuron has its own data, all of the neurons are running the same program. They have the same behavior. So what this means in computer terms is that we've got data level parallelism. Yeah, we're running the same program on lots of data, essentially. Oops, I've just gone forward without meaning to. When I have a habit of clicking on things and it makes it go forward. What happens if I right-click? No, right-click doesn't do anything. Yeah, no, I mean, data level parallelism has an interesting history. You know, they made the first computers with optimizations for data level parallelism in the 70s, you know, the Cray supercomputer or whatever. But anyways, let's not get sidetracked. At the moment, the best type of computers we have for data level parallelism are GPUs, which is why we use these for AI. Cool. So what actually is an artificial neuron? So an artificial neuron really is just a vector of weights. So a weight is just a number. It's just what we call them. So a weight is something it's learned during training, and essentially it's memory of. It's basically remembering correlations with all of the neurons that it's connected to, right? So each neuron has a bunch of input neurons, which is neurons that it receives data from, and it's learned correlations between its inputs. Now, we're not covering how the learning algorithm works. That's out of the scope of this presentation, but yeah, I'll probably just read what I've written. So, an artificial neuron is connected to several input neurons and several output neurons. The behavior of the artificial neuron is essentially just to dot product its inputs with its stored weights, right? So our two vectors that we're dot producting is whatever signals we're getting from our inputs and whatever we have stored. And then so that output is a single number which it then sends to all of its output neurons. An important thing to remember here is the data is traveling through in one direction. So the data is traveling from left to right. Note that the size of ANS is specified in number of weights. So you might hear that, a large language model is a 1 trillion parameter model or a 300 billion parameter model. What they're talking about there is the number of weights. So in all of the artificial neurons, if you were to count the number of numbers in each neuron's vector, that's what they're talking about. But it's also the measure of the number of connections, right? Because the total number of connections between neurons is the same as the number of weights, essentially. Apart from the first layer, I guess. So it's a measure of how many numbers are stored in the network, and it's also a measure of the number of connections between the neurons. Cool, so I can't remember what this slide is, so I'll just read it. So there are many different architectures of how artificial neural networks can be put together and how they're trained. Large language models are powered by the transformer architecture, often called the transformer model, which was invented by some researchers at Google in 2017. The research paper that they published in 2017 is actually available to the public. It's called Attention is All You Need. Anyway, the LLMs that power popular chatbots run on artificial neural networks with hundreds of layers of artificial neurons, each thousands of neurons wide. Which means you're doing very wide dot products, right? So those vectors that we're dot producting might be 4,000 or 8,000 long, right? Lists of numbers, maybe 4,000 long, 8,000 long. Now, 99% of the calculations that are happening, both during training and inference, are dot product calculations. So if you're wondering what the server is actually doing when you ask ChatGPT a question or get an image generated to generate you a picture, most of it is just dot product calculations, because that's what powers the artificial neurons. Cool, so another slide that I can't really remember what I wrote, processing power. So the difference between inference and training, right? So inference is you've got a model that's already been trained and you just want to use it, right? So when you're talking to ChatGPT or when you're using any kind of generative AI model, this is inference, right? It's not learning anything, you're just asking it to do something and it's doing it for you. So for a chatbot like ChatGPT to answer a single question, billions of dot products have to be calculated. And because these dot products are across huge vectors, it requires tens of trillions of total calculations. So yeah, that's true. So training is when you're converting your blank neural network into a trained one which can do useful work. Training requires many orders of magnitude more processing power than inference. It requires months of computer time on exascale computer clusters. This means a cluster doing quintillions of calculations per second for months on end. Yeah, true. Crazy. So yeah, so some comments on hardware. So this part is kind of interesting in my opinion, because with most types of modern software, you don't really need to. I think by the 2000s, computers had got so good that for ordinary programming, like, I don't know, the kind of programming you do for making a website, people cared less and less about performance problems, and you could just do things with high-level languages. So you got a generation of programmers that didn't really care about the low-level details of how computers work. But with this AI stuff, there's like some really big performance limitations and problems you have to deal with, which means that to make progress in AI, they do have to care about how the computer works, because there are just like serious performance bottlenecks. So simulating large artificial neural networks is a very difficult thing to do on a computer. This is why little progress was made on it before the 2010s. That's true, right? People had the idea of simulating the human brain or making an artificial neural network as far back as the 60s, but they didn't have, they were so many orders of magnitude below having enough processing power. Okay, so you might hear that AI GPUs or NVIDIA's GPUs are optimized for matrix multiplication, whereas I told you earlier that most of the processing is dot products. But it's the same thing. Okay, a matrix multiplication is just a way of matrix multiplication is dot products. It's a way of packaging it up in a way that's efficient on the memory bandwidth and memory latency, right? So there's this thing called the memory gap. So the memory gap is basically a problem that's existed. It started in the 80s, right? So processors were getting faster more quickly than the memory was. So the initial solution, the mitigation for that is to have a cache. So the first microprocessor with a cache came out in 1989. And nowadays, the processor cache is crucial, right? Every processor has multiple layers of cache, and this is essential for performance. Now, if your working data set is small enough to fit in the cache, then this might basically entirely solve the problem. However, if your working data set is big, then the cache doesn't really help you. So for certain types of workload, modern computers can be surprisingly slow. And unfortunately, AI runs really badly into that problem. So a traditional transformer model needs access to all of its memory to generate every token. So that would mean, let's say it's a 70 billion parameter model, and it's using, I don't know, let's say it uses 100 gigabytes of RAM. It needs access to all of that RAM to generate every word of its output, because the entire neural network needs to be processed through, right? It needs every layer of the neural network needs to be used. Now, they do sometimes do a thing called a mixture of experts model, but all that means is that you only need dozens of gigabytes to be active at a time instead of hundreds. So even a mixture of experts model has an enormous working data set, which means the processor cache is just useless. So the whole idea of matrix multiply is you're just packaging up a large number of dot product calculations in a convenient chunk of data, which puts less pressure on your memory. It puts less pressure on your memory latency, right? Because to reduce pressure on latency, you don't want to do lots of little reads and writes. You want to do a small number of big reads and writes. But you also want to reduce pressure on memory bandwidth. So to do that, you need a high arithmetic intensity, which means you want to do lots of calculations on whatever data you're reading in. So the whole point of a matrix multiplication is to reduce pressure on the memory. That's the entire point of it. It's a way of packaging up your data so that you can do lots of dot products quickly with putting less pressure on your slow memory. Yeah, so I've got a note here to explain HBM. So HBM simply stands for high bandwidth memory. It's just a type of extremely expensive memory that they use for AI GPUs. It's about 5 times as fast and probably 100 times as expensive or something. But even despite these matrix multipliers and even despite the HBM, the memory gap is still a massive bottleneck in AI. So much so that they say that top of the line NVIDIA GPUs are about 35% utilized in terms of the compute units. I've just gone forwards by accident again. But yeah, I think I was at the end anyway, so yeah. Yeah, the memory gap is still a massive, massive bottleneck, and I'm just trying to emphasize how poorly optimized our hardware actually is for AI. Simulating artificial neural networks is extremely hard for computers. Yeah, so the next slide, summary, right? Yeah, so this slide is just to go over some of the facts we mentioned before. So a vector is just a list of numbers, and it represents a direction and an amplitude in any number of dimensions. A dot product is a calculation to compare the vectors and find out how similar they are, to compare two vectors. Yeah. An artificial neural network, an artificial neuron works by calculating a dot product on its inputs and its stored weights. A large artificial neural network has tens of millions of neurons and trillions of connections between them. So there's a few things we haven't covered. So embeddings and tokenizers, right? So that's basically, let's say it's a chatbot, right? So you don't type a bunch of numbers into it, you type writing into it. So embeddings and tokenizers is how you convert whatever your input is into vectors, because the large language model of itself, the actual artificial neural network, cannot process text or images directly. Everything needs to be converted into vectors first. So yeah, that basically means you've got a layer of traditional software that runs before this job. So you've got a layer of traditional software whose job is to convert data into the right format that the artificial neural network can ingest. Training algorithms, right? So yeah, when you're training your artificial neural network, obviously, so those weights we mentioned earlier, the stored vectors of each neuron, obviously those need to come from somewhere. So that's what your training algorithms are. So you can research back propagation and things. So it's basically a problem of, okay, so let's imagine we're training our artificial neural network and it produces a bad output or a good output. How do you reverse engineer through the neural network and find out which neuron was responsible for that good or bad output? So yeah, that's training algorithms and many other things, right? So this isn't supposed to be a practical guide on how to build artificial neural networks. I just wanted to focus on dot products and how useful they are and go over some other basics. So yeah, I think that's my presentation. I hope you learned something.